Okay, we'll get started with Chapter 11, Seismic Design Criteria. The first order of business is to find our mapped acceleration parameters. We'll use Bolivia as our example country here because they are the most seismically active region we work. And these parameters are mapped for the US within the ASCE specifications, but for Bolivia, we'll use an external research paper, which I'll include in the references below, to read our maximum considered earthquake spectral response parameters. And note that these are percentages of g, or gravity. And there is a short, a 0.2 second acceleration, and a long, 1.0 second acceleration parameter. The next step is to get our design spectral response parameters, which is SDS and SD1, which are 2/3 of SMS and SM1 respectively. And to get these, we'll need to use our adjusted spectral response parameters, which are the SMS and SM1 values, and that are then adjusted based on site classification. And this site classification comes from chapter 20.1 and is determined based on the average shear wave velocity for the nearest or closest 100 feet of soil to the surface. But because we don't have this site-specific data and there is no detailed geological report, we'll choose the default site class D, which is accepted by the specifications. And then with this information, we can return to tables 11.4-1 and 11.4-2 to read our FA and FV values, and then calculate our SDS and SD1, our design spectral response parameters. And you'll notice as we go throughout that there's going to be a lot of variables we're reading off tables based on either the site or the structure we're using. And this is because we're taking this dynamic motion and we're translating it into some static force. So a lot of these values are going to be empirical or data-driven, and it's not going to be a simple statics equation we can use to get the value. So now we'll begin to develop these parameters specific to our structure, because these other parameters were specific to our site. So in section 11.4.5, we find the design response spectrum, or the response period of the structure. Think if you push the entire bridge deck, how long would it take before it returns to its original position? This is its period. So we'll need to estimate the fundamental period of the structure T as TA, the approximate fundamental period from section 12.8.2.1. And remember this graphic from before, and we'll jump to find the approximate period of the structure. And remember, we're just analyzing the abutments here. We're not looking into our cables just yet. So here we have to read two more variables, x as 0.75 and ct as 0.02 from table 12.8-2 for all other structural elements. And then we'll take our structural height, which is the tallest distance from the ground to the seismic force resisting system. In our case, we'll just take that as the distance from the base of the foundation to the top of the handrail cable saddle. When we plug everything in for the abutment, we get 0.15 seconds, which makes sense because we have a very stiff structure. It's basically just concrete masonry. So the final two sections of importance in Chapter 11 are 11.5 and 11.6, which discuss importance factor and risk category. Both these values come from Table 1.5-1 and 1.5-2 and are related to how the bridge is actually being used. So we'll take risk category 2 simply because of the low population density. And because of that, we can read our importance factor for seismic design as 1.0. Then section 11.6 gives us our seismic design category based on both the risk and importance and our spectral accelerations, the design spectral accelerations. So we take the most severe value to govern in this case, but in our case here for our design spectral accelerations, we have seismic design category D for both tables, both options. So this will sum up what we do in Chapter 11, and then we'll move on to Chapter 12, and we'll figure out how to translate these ground accelerations into actual building loads.